Now, layer 2 means data link layer. If you take any packet here, see I have a packet here.
Yeah.
It's a OSPF packet, and it has got layer 2 here. What do you see here in layer 2 header is a destination IP address.
Yeah.
It is a multicast address. How do I know? Two things. There is 5E in the middle. If you have a multicast address with 5E right in the middle of the address, a MAC address, sorry. If you have a MAC address with 5E right in the middle, which is a multicast address. That's the
Yeah.
clue. All right. And the source address is not a multicast address. It is an address of a particular router. This is the address of a particular router.
Okay.
And I also have a clue here saying IPv4 multicast address. What is the connection between MAC address and IPv4? Listen, this is a packet that is sent by OSPF. How do I know it is
Yeah.
OSPF? The 224.0.0.5 is the multicast address of OSPF.
Yeah.
And the OSPF is sending an address, a packet, a hello packet. How do I know whether it's a hello packet or what packet? Open this, you'll see. It's a hello packet.
Yeah.
OSPF is sending a hello packet with a source IP address, and the destination IP address is the multicast address. So if the destination address is a multicast address, which means the packet belongs to many devices, not just one device, a group
Yeah.
of devices. That is what multicast means. So this IPv4 address is used, this IPv4 multicast address is used to derive this MAC address. So this is the
Okay.
automatically generated, dynamically generated MAC address. Now who will be responding to this MAC address? All those devices that have joined OSPF. All those devices that have joined OSPF will have 010056000005.
Yeah.
So this is how the layer 2 header will look like. Layer 2 header has got the source and destination MAC address. So this is
Yeah.
what we see in the capture. Also we see in layer 2 type. What type of packet it is? It's an IPv4 packet. Now why do we see IPv4 information in Ethernet in layer 2? It's inside layer 2 type. Actually, this type in the IPv4 header means what comes next. What comes next is, you see, IPv4, Internet Protocol version 4. So this is the ID 0x08800 means the next header is an IPv4 header.
Yeah.
If I have IPv6, then this number will not be 08, it will be some DD, something like that. So in in a layer 2 header, you don't see too many things here. As a
Yeah.
networking person, you need to know the MAC address resides in layer 2,
Yeah.
and you will also need to know there is a field called type, which explains what layer comes next. The next layer is IPv4 layer. That's
Okay.
all.
Okay.
As a network guy, you need to know.
Yeah.
Now, if you simply open a Google page, ask for a layer 2 header, it will show you more fields than what you see here. Here you
That's right.
just
Yeah.
see source, destination, MAC address, and the type. What about those fields that are not here? Those fields that are not here are not really important for a networking person. Why? Those things are like checksum value and CRC, cyclic redundancy check. Those are all for integrity. Those things will
Yeah.
change for every hop. You will not be able to capture them. When it moves from one router to another, when the other router receives it, all the checksum value, all those things get removed. The things that are kept without removing when it is received are only these three things: MAC address, source and destination, and the type. All the rest gets removed, and when it is sent to another router, again it is added. So you will not be seeing that, and Wireshark also cannot capture those things. Yeah. Now, network people, you should know that MAC address is 48-bit size. 48 binary bits. Now, how many bit of binary is one bit of hexa? Any idea?
48.
No. How many bit of binary is one bit of hexa? One bit of hexa, let's say this is an hexa bit, is equal to how many bit of binary? It is 4 bits of binary.
4 bits, okay.
How? How? Let's see how. Actually, what we are learning is my CCNA.
Yeah.
This is how my CCNA goes. All right. You see, a hexa bit can go from 0 to 9 and then A to F, isn't it?
Yeah.
That is called hexadecimal, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A, B, C,
And
D,
then A
E,
to
F.
F.
So here F represent what? In decimal 50.
15.
F is 50. After 9, A is 10, B is 11, C is 12, D is 13, E is 14, F is 15. Correct. So if I write F, it means 15. If I that's the biggest of one hexabit. That's the biggest of one hexabit. If I need to put the smallest of hexabit, it is 0. Now, the biggest of hexabit is 15. If you need to write this 15 in binary, if I have one bit here on, is that okay? Enough? No.
No.
If I have this one bit on, will that be okay? So this is 2 to the power of 0, this is 2 to the power of 1, which is 2 plus 1, 3. Sorry, 2 plus
3, yeah.
1, 3. But F is not 3, F is 15.
15, yeah.
So only when I have all 4 bits on, it is 2 to the power of 3, 2 to the power of 2, which is 8 plus 4 plus 2 plus 1, 15. Yeah? 15. So you need 4 bits to match with this F. 1 bit of hexa is equal to 4 bit of binary. Do you agree this point now?
Yeah, that's right.
That is the reason why the MAC address is 12 hexabit in size. Why? When you write in binary, it will be 4 times more, isn't it? When you write in binary this F, how many times more? 4 times.
Yeah, 4 times more.
What is 4 times of 12?
48.
Yes. Now let's see the MAC address. Do you see 48 bit or 12 bit? Any MAC address you take, it will be 12 bit. Let me show you a MAC address example. My network, place, network connections, change the adapter settings. Let me take one VM's MAC address. And when you see the properties, no, these details. Here you see the MAC address 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 bits. Because you write in hexa, see 5, 6, this is not binary. Binary will be 0 and 1 only. This is not hexa. So when we write MAC address, we write in hexa. So 48 is turned to 12. MAC address is 12 hexabit in size. What is the size of MAC address? You can answer 48 or 12. If you say
12
48,
hexabits.
it means binary. So when you say 48-bit, everyone understands that you are speaking in the terms of binary. But when you say 12, you need to be very precise saying hexabit. When we don't say binary or hexa, they will think as binary. What's the size of IPv4 address? 32. Correct? IPv4 address is
Yeah.
32. Is it binary? Of course, yes. But I did not say binary. You understood as binary. What is the size of IPv6 address? 128.
128. 128.
But I can also say 32. IPv6 is 32-bit. IPv4 is 32-bit. How is that possible? IPv4 is 32-bit. When you say IPv4 32-bit, it means binary. But when I say IPv6 is 32, I actually mean hexa. 4 times of 32 is what?
128.
Yeah. IPv6 is 128-bit size. When you don't mention hexa or binary, it means 128 binary bits. But if you will write this 128 in hexa, that is how we write IPv6 address. See, for example, IPv6 address is 32-bit, it's a 128-bit. But if you count and see, it will be only 32-bit because it is hexabit.
Yeah.
It is hexa. It's 128-bit size. And when you count and see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, see 4, 8, 32. 1, 2,
32.
3, 4, 5, 6, 7, 8. So 4 times 8 is 32. So when you write in hexadecimal, it is 32-bit. But when you write in binary, see they have written in binary. Oh my God! Starting from this 0 to till this 0, it's 128 numbers. Only zeros and ones. It's not that easy for us to remember and write. That's why the lengthy addresses like IPv6 address and MAC addresses, they're all converted into hexa. When you write binary into hexa, the number becomes smaller or bigger. When we write binary in,
Smaller.
it becomes
Smaller.
smaller, which will be easy for us to handle. That's the reason why the MAC address is in a hexa format. So now what is the size of a MAC address? You can say 12 hexabit or 48 binary bits. Very basic understanding that someone should have about the addresses.
Yeah.
Now, that is layer 2 address. There is a device which uses this address to decide the path. And we call that device as what? Switches. Switches don't decide the path based on your IP address. Switches decides the path using this layer 2 address called MAC address. This is the reason why switches we call it as layer 2 device. Why switches are layer 2 device? Because they forward the packet by reading the MAC address of the incoming packet. They read the MAC address and they forward. They don't care about the IP address because they don't have that knowledge of understanding IP address. They are layer 2 device. The job is to do switching using MAC address. The switching happens. Whereas the routers uses the IP address of the incoming packet, the destination IP address of the incoming packet to decide the path. Right? So that's the big difference between routing and switching. Very simple. Switching means what? Moving the packet by using the MAC address. Who does that? Switches.
Switches.
What is routing? Moving the packet based on the destination IP address. Who can do that? Router. Because router has got the routing table in which you got network information, the destination, the path, and the metric. In switches, all that you have is a MAC table. You don't have routing table. In switches, we have MAC address table, media access control, MAC address table. So with MAC address, the packets can go from one port to another. For example, let's say I have a PC with MAC address. For example, I'm writing a. The IP address of this PC is 10.0.0.1. And this is connected to a switch. Let's say the port number of the switch is F01. And I got another computer here connected whose MAC address is BBB and IP address is 10.0.0.2. Another one here, CCC and 10.0.0.3. Another one here, DDD. Assume this ABCD as MAC address. Now we're going to learn two things from here. One, how switches forward the packet. Two, what are the functions of a switch? Right? Knowledge of these things is very important for protection, though it is not in the CCNP syllabus. But without this, knowing only those 2-3 lines that is mentioned in the CCNP syllabus is waste. Switch listens to the incoming source MAC address field of every packet and learns the MAC address from the source of the packet into the table called MAC address table. LSN, listen. So for example, if A is talking to C, I ping from here 10.0.0.3. So what the PC will do is it will use a protocol called ARP, Address Resolution Protocol, to discover the MAC address of 10.0.0.3. Why? Because in OSI layer 3 you should have a source and destination IP address. Layer 2 you should have a source and destination MAC address. Do I have source and destination IP address? Yes. I'm pinging from here, so that becomes source. Pinging whom? This, destination. What is my MAC address? I know my source MAC address is AAA. But what is the destination address? Do not know, isn't it? We don't know. We do not know the MAC address of 10.0.0.3. V means the computer will not know. Here I have written, you will simply say CCC because you can see. But how do A knows the MAC address of 10003? So it uses ARP. So what it does is, as it is trying to send the ICMP packet, what does the protocol ping uses? What does protocol ping uses?
Echo request.
ICMP, right?
ICMP. Yeah.
ICMP. So as the ICMP is trying to go out, simultaneously ARP will also go and look for 10003 by putting the layer 2 multicast address as a broadcast. 12 times F. See, in layer 3, what is the broadcast address in layer 3?
10.0.03.
No. Layer 3 broadcast address. 255, 255, 255.
255.255.
This is layer 3 broadcast address. What is layer 2 broadcast address? This is the word. How
Yeah.
many times I have written F? It should be 12 times. Because we just learned the MAC address is how many bits? 12 hexabits.
12 hexabits. 12 hexabits.
When all the bits are on, you will get F. In IPv4, when all the 32 bits are on, you will get 8.8.8.8, which is 255.
Yeah.
So this is what called as layer 2 broadcast. Now, it puts the layer 2 broadcast address and sends the ARP request. As this packet enters this port, what it will do, the first job is to listen to the source of the packet. What is the source of the packet? Source MAC address is AAA. So it writes saying AAA is connected on F01. This is how it learns the MAC address. So listening
Yeah.
and learning is the first function that we learn about a switch. Functions of the switch. Listening and learning. Listening and learning is the function. Is a function of the switch. Next. The packet is a layer 2 broadcast packet. So switches will flood it to all the other ports except from where it is coming. Because it's an FFFF, which means to all. The packet will go to everyone. And when this PC receives the packet and opens layer 3, is not matching with its own address. 10003 is not matching with 10002. So this PCB will drop the packet. It will not process it further. Likewise, this guy will also drop it because the destination of the layer 3 address is not matching. Only this is going to process it. When it opens the layer 3 header, it finds that it's an ARP reply, it's an ARP request. Let me show you how the ARP packets will look like. I think I may have some ARP packet here. I don't have any ARP packet here. Wait, I can show you an ARP packet. This is an ARP request packet. You can see address resolution protocol request. And if you see the layer 2, the source address is a MAC address, like we have AAA. And the destination is a broadcast FFFFFFFFF, isn't it? Yeah, it's a layer 2 broadcast.
Yes.
And now the type, it says the next header is not IP, it's an ARP. Earlier when we saw type, it was IPv4, you remember? Here it
Yeah,
is
that's right.
ARP.
Yeah.
And when you open the ARP, it is asking who is 192.168.56.2. Who is that? I don't have the MAC address of this guy. Who is that? You know, this is how the ARP request packet will look like.
Yeah. Okay.
Now let's see how ARP reply will look like. This is how ARP reply will look like. Here it says this is my MAC address. I am 192.160.56.102, and this is my MAC address. It's in the reply. It's an ARP reply. You see it's written here, ARP reply. Request and reply, but the reply is not a broadcast. Okay, so this is going to respond back with the reply saying me CCCC source. So the reply, what will be the source of the reply? CCCC. To whom it is replying? To AAA. The source becomes the destination
Yeah.
here. AAA. Now, as the packet hits this port, let's say this port is F02, F03, F04. When the port hits F03, then switch learns that someone called CCC is connected on F0/3. You see, so this is how the learning of MAC address, listening and learning, listening the incoming source of the layer 2 header, and learning happens. Fine. Now, the return packet is a unicast packet. You saw here, it's a unicast packet. It's not a broadcast. So when this packet goes with the destination MAC address A, who is MAC address A? Then you see switch simply finds A here on F01 and moves the packet to F01. This is what we call it as switching. See, the packet forwarding is not based on the IP address. Actually, the packet has also got IP address, but the ping is not happening based on not our packet. I'm talking about the normal packets. They also have IP address, but the switches in the middle, they use the MAC address to forward. Even here in our example, you're pinging 10.0.0.1, sorry, pinging 10.0.0.3. So definitely there is a source IP address and destination IP address. In the ARP reply, how will be the ARP reply? Source 10.0.0.3, right? That's the reply.
Yeah.
Destination 10.0.0.1, and source MAC address is CCC, and destination MAC address is AAA. Even though there is an IP address in this packet, the switches, they don't need your IP address. As soon as they see the MAC address, they understand where to forward the packet. It forwards the packet on F01 and it gets delivered. This is what we call it as switching. Switching is switches using the MAC address and deciding on the exit port. For that, the MAC address need to be the MAC address need to be updated. Thank you. In the MAC address table, MAC address table needs to be updated table. If any destination MAC address is not seen in the MAC table, if there is any destination MAC address not seen in the MAC table, then what switches will do is it will flood. It will flood.
Yeah.
It will flood so that everyone receives the packet, and only those who have got the destination MAC address matching with its own MAC address will be eligible to process it. All the rest will drop it. So switches listens, learns, floods. Switches will also filter traffic. Flooding and filtering. Switches will also filter traffic. Switches not only floods. When will it flood? When the destination is unknown. When will the switch filter? Any idea? So we have a switch, and let's say all the MAC addresses are updated. BBB is on F02 and DDD is on F04. So we see here all the MAC addresses are fully updated. Now what happens is you're connecting one of the port, let's say F05, to a hub. Now this hub is connected to, let's say, two devices. EEEFFF. FFF, and let's say the IP address on this is 10.0.0.5 and 10.0.0.6. Now let's say I'm pinging from 10.0.0.5 to CCC. Sorry, 10.0.0.5 to 10.0.0.3. The ARP table on this computer will say the destination MAC address is CCC, the source MAC address is EE, the source IP address is 10.0.0.5, and the destination IP address is 10.0.0.3. See, I'm pinging from here to C. The destination MAC address is known from where? From the ARP table of my computer E. You're okay with this, right? I'm pinging
Yeah.
from here to here.
But it doesn't know the destination MAC address, isn't it?
Let's say earlier it sent an ARP request. It has learned in the ARP table.
Yeah. Okay. Great. Yeah.
So now it has got the ARP entry. So what it does is it moves the packet via the hub. What hub will do usually? Whatever it receives, it will flood it. It will flood it via this way as well as this way. Now when it is flooding like this guy has learned the MAC address of 10.0.0.5 in the ARP table. Likewise, whoever received it might have received. Now what I want to say is the packet that went here will be dropped. Why? The destination IP address does not match here. Not only destination IP address, even the MAC address does not match. So this PC receives the packet, but it drops it without any further processing. As soon as it finds the destination MAC address is mismatching, it drops it. Right, because I put FFF, don't think that I have put layer 2 broadcast address. Now let me then put it as GGG. So the incoming packet's destination MAC address must match with the local MAC address, only then the packet is for me. Otherwise, it's not for me. So this PC drops it. Now when the packet goes to the switch F05, F05 now learns that there is someone called EE on F05. Likewise, okay, now it will look into the destination MAC address. It is CCC. It knows where is CCC. It forwards the packet, so the packet comes down here. This is simple forwarding. It's not filtering. Now we are trying to learn filtering. You see, this GPC wants to talk to E. Assume G wants to talk to E. Now what will be the source IP address and destination IP address and MAC address? The source IP address is going to be 6, the destination IP address is going to be 5, and the source MAC address is going to be GGG, and the destination MAC address is going to be E. Am I right?
Yeah.
Okay. The source is GGG and the destination is EEE, And the source IP address is 10.0.0.6 and the destination IP address is 10.0.0.5. Because I'm pinging here 10.0.0.5, it knows the destination IP address and it looks into the ARP table of the Windows machine. The Windows computer says the ARP, the MAC address of 10.0.0.5 is EEE, which is learned earlier. See, ARP table, when it learns now the MAC address, it will not erase for 1 hour. Even though when there is no communication, for 1 hour the MAC address will stay. If you communicate to the device every half an hour, then it will stay for long. When you don't communicate for 1 hour, the MAC address in the ARP table will stay. Whereas in the switches, the MAC address table will refresh every 30 minutes. This MAC table, if we are not communicating, this will get erased after 30 minutes. Again, it needs to be learned fresh. Okay, now let's go to this story. Now G is talking to E. The packet arrives to the hub. What hub will do? Flood it. A copy will go to here. It will be accepted. Happy leave. But the copy that is going here, what will happen? When the packet goes to F05, the switch learns that there is someone called GGG also connected on same port. Correct or not? Of course, yes.
Yeah.
F05 is connected to both GGG as well as EEE. So what it has learned is correct. So what we learn from here is there can be more than one MAC address on the same port. That you should not forget. This is very basic fundamental. There can be more than one MAC address on the same port. And this is one example. And this time, will the packet be forwarded? See, packet is coming from GGG. It wants to go to EE. When it checks the source, it is GGG. When it checks the destination, it is EE. It is the same port. Will it forward? No. It is going to filter.
Okay.
There is no point of forwarding because the destination is nowhere on the switch. The destination is the same port where the source is, according to the switch. So switches will not forward. So the functions, three main functions of the switches are listening and learning. Correct?
Yeah.
Number two, forwarding and filtering. When will it forward? When it finds the destination MAC address in a port. Forward. When will it filter? When the source and destination MAC address are in same port. It will filter. The third function is flooding. When will it flood? When the destination MAC address of the packet is unknown to the switch. Switch is going to flood it. Right?
Yeah. So in that. Yeah.
Carry on question.
So in that case, so what happens is now the switch is filtering the packet from F05. Now in that case, the hub is forwarding that, isn't it? Hub is forwarding the packet to the correct destination.
Yeah, hub is not forwarding, hub is flooding it always.
Flooding, yeah, that's right, flooding.
So if I have more than two devices, then all those devices would have got those devices that are connected,
packet,
yeah. So they all might have dropped it except this one, all others would have dropped it. So we are not learning hub here. We are just using the hub to understand that there can be more than one MAC address connected to the same port on the switch. If that is the case, then the filtering will happen if the source and destination are in the same port. Is it easy or confusing? Whatever. Ask me questions.
Yeah. So
if you are stuck somewhere.
So basically, I understand. So basically, what happens is like now, let's say the switch learned the MAC address GGG, and the switch learned the MAC address of EEE. Now it has the the MAC address and the port destination the port for those two IPs. Now what it does is basically it receives the packet from the F05.
Let me help you. See,
Yeah.
when I ping from, let me name it as G and E. When I ping between this is how the packet will look like. Source IP, destination IP, source MAC, destination MAC. Now when this packet approaches the hub as usual, it will broadcast to everyone, and a copy of broadcast is also going to F05 to which the hub is connected. F05 on the switch which is connected to the hub. Yes or no? Will it go or not?
Yeah, it will because
go.
it's flooding.
Yeah, it will go. Now what happens? Now switch will try to look into the packet. Switch finds that the source is GGG, which I have already learned, so I don't need to learn again. And when it is about to see the destination so that it can forward, surprisingly the destination is also on the same port. Then switch is going to filter it.
Yeah, that's right.
It won't send in a reverse path like that. It is already coming in this direction, so it won't send it back in the same direction because it's not necessary. So switch is going to simply filter it. If the destination is DDD, when you're pinging from G to D, this time, because the destination is in another port, F04, it will forward. It won't filter, it will forward. It forwards.
That's right, yeah.
So functions of a switch: listening, learning, forwarding, filtering, and flooding. Flooding is needed only when the flooding is needed only if the destination MAC address is unknown to the switch. Switch always learns the MAC address as the packet comes inside. All right, fine.
Yeah.
This is just to understand what the switch does. What is switching? Switching is moving the packet based on the MAC address information on the packet. I also showed you how the packet will look like. It has got a source MAC address, the destination MAC address. So this is how the packet will look like. Only after processing this layer 2, it will process layer 3. But if it is a switch, as soon as it processes layer 2, it will know where to forward by looking into the MAC address. It will know to which interface it needs to push it out, and it will push it out. So there is no need for looking into layer 3 header. It won't look into layer 3 header. Switches, they don't process layer 3 header because they only understand MAC. In case if the destination MAC address is not in the MAC table, switch is simply going to flood it to all the ports except from where it is coming from. They're entering the port which it is received. Except the port in which it is received, all the other ports will be getting this flooded packet. And only those devices that matches the destination MAC address will receive, other device will drop. Right, this is what we have. See, the ports of hub, they never learn MAC address. So when you have some ports like this on a hub, this is the maximum number of ports that you will see in a hub. In a hub. See, all those devices that have got 8 ports, that doesn't mean they are a hub. No, that's not the meaning I'm telling you. But if you take hub, no hub can have more than 8 ports. You got also some switches with 8 ports. Because of the 8 port, you cannot call that as hub. Switches. Hub cannot have more than 8. The switches can have even 300 ports. Now, the reason why hub is limited in number of, though we are not using hub, the reason why I'm talking about hub is to understand collision domain and broadcast domain. These two words are very important for us to understand. You see, the hub's internal architecture will be like this. We call this as bus topology, right?
Yeah.
This is what you will see inside logically. Now, when you have only one wire as a backbone, this is a single wire which is responsible to take packet from A to C. Also, this is the only wire responsible to take the packet to every other computer. So, in another simple word, if you are doing an unicast, if you want to go from A to C, which is a unicast, this is the only backbone you have to use. There's no other backbone. There's no other path. And if you want to talk to everyone, like B, C, and D, it's the same backbone. There's no other alternate paths. Which means whether you are willing to flat it or send it to a single device, there is no option other than using this. So how it works is whatever touches this line, this link, the backbone, that will be given to everyone. So when you send a packet to C, destination C, as soon as the packet hits this backbone, a copy of it will go to everyone, which is what we call as broadcast. Hub will always broadcast because logically a bus topology is what you have. In another word, what I should say is all the ports are in one controller, this backbone. Similar to this backbone, you have a controller which is connecting all of them. So all 8 ports are connected to one common backbone, one common broadcast domain. What is a broadcast domain? Or when a device sends a broadcast, if it will reach all the devices in this switch, which means the ports of all these devices are in single domain, single group, single broadcast domain. See, the word domain can also be interpreted as controller. The broadcast controller. The broadcast controller, the broadcast domain, the broadcast controller. To control broadcast, this is the only backbone responsible. Not only that, to control the collision, it's the same backbone. If A is talking to C and if B also want to talk to A at the same time, when A talks to C, B wants to talk to A There are chances of collision, but the collision never happens. It is because it has got one collision domain that controls the collision. That's why we call domain as controller, collision controller. We got one collision domain to control the collision. What is that? Carrier sends multiple access collision avoidance method. So the operating system that is controlling the hub has got this in it. What it will do, if A is talking to C, it will not allow B to talk to A. It will make B packet to wait here for a random period of time. So once A finished talking to C, it refreshes the timer and B now allowed to talk to A. So at any point of time, only one conversation you will see between these devices, any one conversation. More than one is not possible because the carrier sense multiplex access collision avoidance won't permit two conversations to happen, because if it happens, collision will occur. To control the collision, carrier sense multiplexes collision avoidance allows only one conversation at a time. So hub has got one broadcast domain, one collision domain, whereas switches have more collision domain and more broadcast domain. Right, let's say these are all the ports of the switch. Switches have got one collision domain, so one broadcast domain by default, and let's say you have 20 ports here. I don't know how many ports I have drawn there. Assume next we have 24 ports, 24 ports. Then I have 24 collision domain. How is that? Every port on a switch can learn the MAC address. As a result, if someone called A connected here wants to talk to someone here called KKK, the switch knows where is A and where is K because the MAC table is updated. When the switch knows where is K, will it flood it? No.
No.
It will take a unique path to reach K. So this is not going to cause collision. Collision will occur only if everyone uses the same backbone. In a hub, you have one common backbone always. You do not have another option. Here you have an option because as soon as you learn the MAC address, you know who is connected where, and you can have a dedicated path to reach from A to K, from A to D. You can take a unique path, which avoids collision. How many ports I have? 24 ports. Then I have 24 collision domain because each port learns MAC address. Each port can have a dedicated path with all other ports when it has got MAC table binded to the port updated to the MAC table. MAC addresses that are binded to the ports that are updated to the MAC table makes this to have a dedicated path instead of having one common backbone. So here you see there is no carrier sense multiplexes collision avoidance. We don't follow this one. This is slow. Carrier sense multiplexes collision avoidance is slow. Why? Only one conversation at a time. to avoid collision. Whereas here, because you got your own dedicated path, once you learn the MAC address, you can logically form paths. Any number of conversation can be allowed. So conversation happens just like that. There is no collision because everyone takes their own path. But we also learned that when switch do not know the destination, it is going to do what? Flooding, broadcast. So what I'm coming to say is, even though switch have got a separate path for each destination, it also has got a common backbone like a hub connecting all, which will be used only if the destination is unknown. This red line will take data, or data will be forwarded to this red backbone only if the destination is not found in the map table. That is why we say one broadcast domain. And if I have 24 port, then 24 collision domain. If I have 48 port, then 48 collision domain. But how many broadcast domain? Only one.
One.
That one is only for taking the traffic which is going to some unknown destination. So anything that hits this backbone will go to everyone. That is what called as flooding, right? You go to everyone. Now, what if a device connecting here is sending a packet with unknown destination? Destination is not known to the switch. The device that is connected here also sends a packet which has got some unknown destination. So both the unknown destination packets are flooded on the same backbone, which is a rare case, but if it happens, there are chances of collusion. So how does the collision avoided? See, this is very rare chance to sending broadcasts at the same time. Even if they send, they don't get collide unless there are too much of computers using the flooding method. The flooding only now this device and this device is flooding. All the rest are having a dedicated line to communicate. Only when there is 10, 15 devices at the same time trying to use the broadcast domain, there may be a collision. Now, how does the collision control here? Carrier sense multiple access collision detection method is used. In switch, only when the collision is detected, then all will go silent for random period of time. And they start again conversation through this backbone. Then there won't be collision. So, in short, switches are fast because they do not wait for someone to allow them communicate. They keep communicating, they keep flooding if there is a need for flood. Only when there is a collision, immediately everyone who was flooding, they all stop for random period of time. Random period of time, not same time interval. And then they start their conversation, one after the other. In that way, collision is avoided. So there is no delay here. Many number of conversations at the same time happens here, but whereas here only one conversation at a time. Switches have got one broadcast domain and 24 collision domain. What about router? Router is a layer 3 device. Let's say this is F00 interface, fast Ethernet 01, fast Ethernet 02, fast Ethernet 03. And the IP address on this is 10.0.0.1, 10.0.0, sorry, 20.0.0.1, 30.0.0.1, and 40.0.0.1. The router is going to maintain a routing table saying 10. This is what we call this routing table, which has got the uh, information about what network is connected on which interface. You see, if there is a switch here having a lot of 10 devices, one, two, three, four. Now, assume that this switch is flooding. The switch is flooding. What is the source MAC address and destination MAC address? Definitely it is going to be one of the MAC address within this 10 because it's flooding. Layer 2 switch is flooding.
Yeah.
When the packet arrives to the port here, it stops flooding there. It says, hey, from where you're coming, 10 network. Where do you want to go? Another 10 network. Well, I'm not going to forward you, I'm going to stop you. The flooding, the broadcast is being controlled here. There is no chance of collision also. Collision is also controlled. How? If this is going to talk to someone here called 30002, it may be flooded on the switch side. Assume that there is no destination MAC address known. The packet arrives to this port. The router will say, if you want to go to 30 network, you should exit on F02. So there is no collision here. It simply goes out on this port. There is no chance of collusion. To go to 30, you have a separate path. To go to 40, you got separate path. To go to 20, you got a separate path. From 20 to 30, you got a separate path. So there is no chance of collusion. What I have learned here is every port stops the broadcast, which means every single port have got a broadcast domain. If it is a 4-port router, then 4 broadcast domain. And if there is a 4-port router, then there is 4 collision domain also. 4 collision domain and 4 broadcast domain on a router. On a switch, only 1 broadcast domain and n number of collision domain, where n stands for number of ports on the switch. Whereas on the router, there is n broadcast domain. Sorry, there is only 1 broadcast domain and only 1 collision domain, whatever the number of port may be. The collision domain and broadcast domain is always 1 and 1. Did you understand what is broadcast domain and collision domain now?
Yeah. Yeah.
Now there is a question which you will see in interviews, especially in European countries. You know, when you apply for a job through a job companies, consultant companies, they conduct online tests before processing your profile. So
Yeah.
you will see this type of question in such interviews in European countries. I don't know about other countries, France and London, the type of job consultant companies, they have this type of question. But I'm drawing as a diagram, but they will explain in words. I'm drawing as a diagram. See, you have a hub, and you got a switch. And the number of ports on the hub is 4. And all 4 ports are connected to 4 devices. See, whatever I'm drawing and explaining, you will be seen there in the words, not as drawing.
Yeah, yeah.
And then one of this port is connected to the switch, and switch has got 24 port. And all the 24 ports are connected with some device. Now, what is the total number of collision and broadcast domain? What's the total number of collision domain and broadcast domain? Have you come across this type of question?
Yeah.
Where?
So the hub is one broadcast domain, and the switch is another broadcast domain. So there's two broadcast domains, if I'm not wrong.
Okay, how many collision domains?
Collision domains. So hub is one collision domain, and the switch has 24 ports. So there's 24 collision domains. So is it 25 collision domains?
Okay, now let us discuss the right answer. You see,
Yeah.
when I was explaining broadcast domain, what did I say? I said when a flooding happens, when a broadcast happens, the number of devices that will get impact, or all those devices are in same broadcast domain. Say for example, if I send a broadcast here, or when a packet goes when it is when the anyway the hub is going to broadcast, and the broadcast will go definitely up to this, and the broadcast continues because it's a broadcast packet, it's a layer 2 broadcast packet, it will continue to all 24 port. So the broadcast that happened here, it goes till the end of the last device on that switch, which means they're all in one single broadcast domain. Is there anyone
Right.
stopping in the middle? No. No one is stopping the traffic in the middle, which means they're all in one big group, isn't it?
Yeah.
So it's not two broadcast domain, it is only one broadcast domain.
One broadcast domain.
Now the collision domain is again the same thing. The common backbone of this one, the logical backbone which is used for collusion, is also on this port, which is connected here to this backbone, which is also responsible to control collision. So you cannot say 24 plus 1 because this has been extended down here. This is only 24 collision domain. The collision controller, it's the same backbone.
The same backbone, okay.
For this one. And that backbone is extended to this backbone. So it merges as one. This is 1 and 23. 23 plus 1 is 24. So it's not 24 plus 1, it is 24. And it is not 2, it is only 1. Okay, now same diagram, but in the middle I'm going to keep a router. Now how many collision domains in total? How many broadcast domain in total? See, every port of the router has got a collision domain and a broadcast domain, correct? So this is one broadcast domain. This is another broadcast domain because this port is extended up to here. So two broadcast domain. It is not like 2 plus 1 plus 1. It's only 2.
Yeah. 2.
And the collision domain also, this is one collision domain and this is 24 collision domain. Here you will get 25 because the collision controller is up is on this interface, and here also you have. Here also you have.
Yeah,
So this
that's
is
right.
one pollution domain. This is 24. 24 plus 1 is 25. Whereas here it is only 20 for the previous one. Sorry, it's not that. I erased it. Yeah, so like this, there are a lot of fundamentals that I have delivered there in the CCNA videos. According to me, more than CCNP and CCIE, CCNA is important because that is where you learn the actual networking concepts, logics. This NP and the IE are just the cream on top of it. So I showed you where you can learn these things. Whenever time permits, go through those videos. All right. And in our next class, what we are going to learn is the STPs, VLANs. You have time now what to study. I have shown you what
Yeah.
all you missed in your CCNA. And I have shown you where you can get it and comments that you can fill the gaps. So I'm going to start from somewhat, not a zero level, somewhat intermediate between CCNA and CCNP level, called VLAN. From VLANs, I'm going to start tomorrow. Very good
Okay.
fundamental. From VLANs and then trunk ports and then STPs. Then we hit the RSTP and MSTP, which was there in the syllabus. So this is how we go. Only then it will be a complete knowledge for you. Do you like this way?